Okay, so let's continue on with our discussion of polynomial and rational functions. This time, though, we're talking about polynomial and rational inequalities. Now, there are two approaches to solving these polynomial and rational inequalities. One is graphing approach, which does require you to graph it. The other one is algebraic. Now, graphing is going to take a longer time to do this, so you got to do everything we've done in previous lectures, and in addition do what we're doing in this lecture. So I'm just going to say with algebraic method. Okay, feel free to read the textbook for the graphing method. Now let's begin with actually an example. I'm going to do several examples, about 5 examples here. So in our first example, let's say I'm going to have a polynomial inequality that looks like this. Negative 12x greater than 0. Now, two things absolutely must be in place for us to solve these polynomial inequalities. Number one, we have to have a 0. This must be 0. It must be what it is. If it's not, you add subtract it from both sides. Okay, to make it 0. Must be 0, which it is. The other thing is the polynomial must be factored. Those two things. The 0 on the right and the factor on the left. 0 on the right has priority. That's number one. Number two, factoring. So let's factor this one. I can factor the GCF, and that will make it x squared, negative 4x minus 12, right? Greater than 0. Now, anything that's greater than 0 means positive, right? So keep that in mind. Now, we're going to continue with our factoring. Inside the parentheses, the trinomial, the quadratic expression is factorable. X minus 6, x plus 2. Those will be the factors. All right. Now, at this point, here's what we want to do. And that's why it's important to have a 0 for what we're about to do. In our next step, we're going to create a sign chart. We're going to look and see what makes each of these factors 0. And x would be 0 precisely at 0. X minus 6 would be 0 at x equals 6. And x plus 2 will be 0 when x is negative 2, right? So there we have these. Okay, now, what do we do next? So once we have these, identify these values, next we're going to pick what we call a test point. Oh, and by the way, because we have greater than 0, notice at 6, we get exactly this whole left side becomes 0. And because 0 is not greater than 0, so we do need to make these points on the number line. We can create them using open circles. That means it doesn't equal to 0, because we don't have that. Now, to start with, if there was equal sign there, then we no need for that. We'll make these solid points. Now, next, what we need to do is we need to pick what we call test points. So, for example, to the right of 6, my test point would be 10. So let me choose 10. And you can plug in a 10 here, here, and here in each of those factors. Or you can go to the original and plug in a 10 there. Remember, these expressions are equivalent expressions. I'm going to go to the factored form and plug it into this expression. So when you plug in 10 for x, that's 10, a positive value. 10 minus 6 is 4, isn't it? Throw away the number, keep the sign. And then 10 plus 2 is 12. Throw away the number, keep the sign. So with the choice of 10, I'll be multiplying a positive number here by a positive number. And 3 positive numbers will multiply to a positive. Therefore, the sign for that segment of the number line will be all positive. What is the significance of plus, plus, plus like that? That means any number beyond 6 you choose, you will get a positive value for that expression. And you can try it. Choose x to be 7. You're going to be getting a positive number. Plug in a 7 there, and you will see the value will be positive. Now, between 0 and 6, I can choose a test point, for example, 5. And then I'm going to plug it into this expression again. Okay, now let me start all over. Plug in a 5 for x, so that's going to be positive. A 5 for x minus 6. 5 minus 6 is negative 1. That's just negative. Remember, keep the sign, throw away the number. 5 plus 2 is 7. That's positive. So I'm multiplying positive by positive. The result will be negative. Negative, 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 negative. See how that works? So again, we're looking at the sign on that polynomial inequality between those values on the number line. Now, for these polynomial inequalities, if we don't have repeated factor of even multiplicity, in other words, for instance, you don't have x plus 2 squared. That's what I mean by even multiplicity. If the exponent is 1, which is the case here in my example, or odd exponents, 1 or odd, then this will happen. The signs will alternate between those segments on the number line. But with even multiplicity, just pick a test point. The sign will not alternate on either side of the 0 with even multiplicity. So you got to be careful again. And there we have it. The selected test points between those values on the number line. Now, we're looking for greater than 0 means we're looking for positive values of this expression, right? Well, positive values happen here and here. True. Therefore, what is the solution? The solution in interval notation will be from negative 2 to 0. I'm going to write that. Negative 2 comma 0 union with this segment. And in that segment, the numbers go from 6 all the way to infinity, right in here. 6 to infinity. And there you have it. That is the solution to this inequality. Good. Let's take a look at another example. Now, in this next example, I'm going to actually look at rational inequalities. So for polynomial, again, you do exactly what I did here. Make sure you have these two things in place, and then you identify the factors and do what I did. Remember, any factor that if this inequality has equal sign, then all these open circles will be solid circles, and the parentheses turn into brackets as such. You see that? That would be the difference if this was, let's say, greater than or equal to. All right. Now, let's take a look at another example. This next example, I'm going to make it a rational inequality. A simple one at that. So I have the 0 on the right side, and the left side is in factored form. This time, both the top and the bottom must be in factored form. And x plus 1 is a binomial factor. There's nothing I can factor there. So let's take a look at this one now. And we're going to draw a number line. Here's my reference point 0. Now let's see what makes the top 0, x plus 1. And negative 1, right? Negative 1 plus 1, 0. And make that open circle because the inequality is greater than. It doesn't have equal sign. And then x minus 1, what makes the bottom 0? 1. And here's 1. Now, when we say 1 makes the bottom 0, this will in fact give us a division by 0, correct? And remember, for rational expressions, fractions, denominators cannot be 0 because we cannot divide by 0. So, regardless of what the inequality is, greater than, less than, greater than, equal, less than, equal, anything that makes the bottom 0 will be an open circle. Okay, so this will be an open circle. It's just the fact that I have greater than, let me actually change it. I'm going to make it greater than or equal to. How's that? There you go. Now, see that 1 in the denominator is still going to be open circle, but the 1 to the left of it, -1, is now solid circle. There. The significance of open versus closed circle. Open circle, the value cannot be included. Closed circle, the value may be what it is. And then we go through our test points. Your test point could be any point of your choice other than what 1 and -1 are. Okay, so I'm going to pick 0. 0 plus 1, 0 minus 1, that gives me 1 over -1, negative. Negative, 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 negative. And the minus, that tells me no matter who picks what, between -1 and 1, we will all get negative fractions. The numbers will be different, but we all get negative values. Beyond 1, let's pick 2. It's going to be 2 plus 1 over 2 minus 1. That's 3 over 1, positive. Notice how again it changes sign as we hit those numbers. And you can try this will be positive. I knew that's going to happen because I don't have even multiplicities on these factors, so I would expect the signs to alternate. Now, let's check this one out. Greater than 0 means positive, right? Well, we get positive here and we get positive here. Therefore, the solution to this is going to be -infinity up to -1, including -1, union this segment, which runs from open parentheses 1, because if you choose 1, you get division by 0. Can't do that. 1 to infinity. And there we have that one. Okay. So here is the solution to that inequality. Nice and simple. All right. Let's take a look at another example. In this next example, suppose I have an expression that is in factored form, again, a rational expression. X minus 2, x plus 2 divided by x less than or equal to 0. This time less than means negative. So we're looking for negative values or of the fraction. Okay. Let's see what makes the top and the bottom 0. The bottom is 0 when x is 0, right? And that's going to be an open circle. It doesn't matter what the equality here says. We cannot divide by 0, so that kind of trumps everything. In the numerator, a 2 makes the first factor 0. So here's 2. -2 makes the other factor 0. Correct? And there you go. So we have partitioned our number line. Now we need to pick our test points. So our test points, pick something here or here, 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 if you like. I'm going to pick, let's pick 5. I'm going to go in the factored form. 5 minus 2, positive 3. 5 plus 2, 7. And divided by 5. 5 is positive. So you're doing a positive times positive divided by positive. The whole thing should be positive. And there you have plus, 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 plus. And because in between I don't have any factor that repeat with even multiplicity, so I'm going to do this. You see that? Without picking test points. Or you're welcome to pick a test point. Pick, for example, 1 here. Plug it in. 1 minus 2 is negative. 1 plus 2 positive over 1 positive. Negative times positive is negative. Divided by positive gives you negative. You see that? So you can choose a test point, but you don't have to for these. The ones I'm doing anyway. Now, negative, we get negative numbers in that segment and in that segment of the number line. And if you throw in infinities at both ends of the number line, it will make your interval notation go a lot easier. So for these segments, the interval notation is from negative infinity to negative 2. And remember, at 2 and negative 2, these are in the numerator, so these are solid, right? Because I have equal sign, right? This was included to begin with. So I have from negative infinity to negative 2, and we put bracket here. And then the negative picks up from union from 0 to 2 close bracket. And that will solve this inequality. So just like polynomials, you gotta have 0 on the right and factored form on the left. Now, next example, what if I don't have 0 on the right side? Let's take a look at one of these. Over x plus 2 and less than or equal to 2. So if there's no 0 on the right side, remember that takes priority. And we have to subtract 2 from both sides. And I gave you the denominator of 1 so I can combine fractions. I need to get LCD. The LCD is x plus 2. Therefore, this is 3x minus 5 over x plus 2 minus 2 times x plus 2 over x plus 2. I'm giving it a numerator and denominator x plus 2 so I can choose the LCD. Remember, we can only combine fractions that have the same common denominators. So here's my common denominator of x plus 2. The first fraction was 3x minus 5. The second fraction, here's a minus in front of that fraction line, which will distribute to both terms in the numerator. Therefore, it becomes a negative of 2x, right? And negative of 2 by 2 is negative 4, less than or equals 0. And we can combine like terms in the numerator. That will be x minus 9 divided by x plus 2 less than or equals 0. There. So that was all the legwork because we had 2, not 0. Now, we're going to work the boxed in inequality. Let's do our routine. What makes the top 0? 9. So let's say this is 9. What makes the bottom 0 and negative 2? This is negative 2. In the numerator, 9 would be a solid circle because at 9 you get exactly 0. In the denominator, negative 2 will be an open circle. Doesn't matter what inequality says equal because I cannot divide by 0 at that point. Again, it overrides what the inequality is telling me to do. Then I just need a test point, don't I, for this one? So for my test point, I'm going to choose 0 as an easy test point. And I'm looking at this fraction. 0 minus 9, negative. 0 plus 2, positive. Negative over positive is negative. So I don't care about the number, just sign on that number. So it'll be negative, and I would expect these other segments to be positive. You're welcome to choose a test point here, a test point here, and verify what I just put in. Okay. Now, less than 0 means negative, right? Well, negative segment of the numbered line is right here. It's between negative 2 and 9. So that's parentheses negative 2, comma 9, and here's the bracket. Therefore, the solution for this inequality has solutions between negative 2, not including negative 2, and all the way up to 9, including 9. At 9, you'll get exactly 0 in here. And if you plug in a 9 up here, you should get 2. Try it. 9 times 3, 27, minus 5, and then 9 plus 2. That's 27 minus 5 is 22. 9 plus 2 is 11. 22 divided by 11 is 2. Is less than or equal to 2. See? It's true. It's equal to. So it works. And there you go. Now let's finish this up with a slightly more exotic expression, but one that is kind of fun to do. I'm just going to increase some of the factors here. Now this one seems very simple, but a little tricky here. Okay. And I'll show you why it's a little tricky here. The reason I say it's a little tricky because, see, I have even multiplicity at 0. Because, and let's make this straight greater than or equal to 0, so I don't have to subtract a number or add a number to change things up. So the first thing we do, let's do our number line. And here's my reference point 0. Which happens to be what makes the numerator 0 because I have equality there. So that's going to be a solid circle at 0. Okay, now the other zeros. 3 plus x. Well, negative 3 makes that a 0. So here's negative 3. It's going to be solid because it makes the numerator 0, denominator non-zero. The ratio is 0. X plus 4 and negative 4 makes that factor 0, correct? And 0 divided by non-zero is 0. And then we go to negative 5. So here's negative 5. Oh, that one cannot be solid, right? Even though the inequalities is equal. Why not? Because we have division by 0 at that point. You see that? That has to be open. And then x is equal to 1. At 1, the circle is going to be open circle because again, division by 0 will happen, which is undefined. And there we have those segments on the number line. Now, because 0 has even multiplicity, we need to pick a test point. I'm going to pick negative 1. Whatever the sign turns out to be here, it will be the same sign on this side, okay? Because of the even multiplicity. So let's do negative 1. Remember, I'm going in here with a negative 1. You're welcome to put negative 1 or just do the sign. I'm going to put negative 1 because most of you probably like just doing that. 3 minus 1, negative 1 plus 4. Negative 1 plus 5, negative 1 minus 1. There. Let's go through. The bottom, this is going to be 4. That's 2. Negative 2. 4 times negative 2 is negative 8. Done with that. In the numerator, negative 1 squared is positive. 3 minus 2 is 2. 2 times 4 plus negative 1 is 3. So that's positive 6. The ratio is negative 6/8. And I know you can reduce it to 3/4, but remember, the sign is all I care about. All we care about is the sign, not the numerical value for the expression. Okay, so between 0 and negative 3, the ratio will be negative. Now, on the other side of this, it's not going to be negative. It's not going to be positive. It's going to be negative again because x squared, that 0, has even multiplicity. Feel free to put a test point 1/2 and try it if you want to. I'm not going to. It's going to take time. So there we have that one. Again, that was with negative 1. Let's go beyond 1. So beyond 1, I'm just going to go, let's say 2. And then we're going to redo this expression. That's going to be 2 squared times 3 plus 2 is 5. 2 plus 4 is 6. Notice it's all positive, right? In the denominator, we have 2 plus 5 is 7. 2 minus 1 is 1. The product is positive again. So we have positive over positive. That gives me positive. We do not care about the magnitude of these numbers, only the sign. All right. And then you can try something here and something here between -4, -5, and below -5. And for these, you should get here plus. It will alternate in because there's no multiplicity. There. I should say no even multiplicity. And that's interesting. Okay, let me throw in infinity at the ends of the numbered line. That will help me with the interval notation. Now, greater than 0 here. Greater than 0 means positive, correct? Positive. We get positive here, and we get positive here, we get positive here. So there are actually 3 segments. Oh, and here's the other tricky part here. Remember, or it can be 0, correct? Well, didn't we get 0 as x equal to 0? That's not an interval, but actually a value. When x is 0, that whole thing is 0. So we need to include 0 in our solution. So this is cool. Here's what this is going to look like. The solution is going to be from -infinity to -5. Parentheses on both. We always put parentheses on infinity and -infinity. It doesn't matter whether you include it in the inequality equal sign or not, because we don't know what those numbers are. They're just symbols, right? Infinity is not a number, but rather the behavior of a number. That's what that is. Okay, in this case, it means very large. That's all that means. All right. Took care of this segment. Let's move on to that segment. That segment lies between -4 and 3. So we're going to go union, bracket, -4, comma, -3 bracket. True? And there we got that one. Next, we need to pick up that 0 by itself. We put it in a set notation. You see that? That set 0 is a single value. We need to put it in a set. There it is. And then we're going to union that with this segment, which runs from 1, parentheses 1, all the way to infinity. Now that is exotic, folks. That is so cool, isn't it? All right. Fantastic. And there's a solution. When was the last time you had interval notation that looked like that? Yeah. What we do now? Okay. So there you have it. I managed to keep this video under 30 minutes, and I like to keep it that way. So I'm not just going to keep talking about this. So please review these exercises again. Remember 2 important things. 0 on the right side, factored form on the left, regardless of whether you have polynomials or rationals. Okay. And we are done with this lecture. Thank you for watching, everyone.